Okay, before we go over the homework I signed last night, I'd like to finish going over what we were talking about yesterday in class. So we were talking about electromagnetic induction and how Faraday found that when he moved a wire in a magnetic field, that the wire then would register that there was a current flowing through it. I know this diagram is not nearly as good as the one I drew on the board yesterday. Yeah, right. But this was what I was trying to draw on the board yesterday. So there's the north and the south, the wire moving in the field, and there's the galvanometer set up to measure the current. Okay, and remember the galvanometer can measure a very tiny current, and so that way it can pick up any little traces. If the wire is stationary, no current will flow. So it has to be moving with respect to the field. And if you move it down, the current will flow one way, and if you move it up, the current will flow the other way. And if we're thinking conventional current, and I'm thinking conventional because I'm holding the iPad with my other hand, then you point your fingers in the direction of the magnetic field, and your thumb in the direction of the way you're moving the wire, and the current comes out of the palm of your hand. So in this case, the current then would flow into the page. If you move the wire up, finger still in the direction of the magnetic field, but now your thumb upward, and the current would flow in the opposite direction out of the page. So it's palm rule 3.0. That gives us the direction, and the only difference is now your thumb is pointing in the direction the wire's moving, and the force comes out of the palm of your hand. And their thought when they did this was then the force would be what would be pushing the current, pushing the charged particles, making them create a current. If we think about what are the things then that are going to affect the size of the current, we talked yesterday, it was the magnetic field, it was the length of the wire in the field, and it was the velocity with which we move the wire. Velocity because the angle between the field and the direction of the motion come into play, right? It's going to be cross multiplying. The size of the current is going to depend on how quickly the wire sees the rate of change of the field. So I'm saying you're moving the wire, but you could really also cause a current by moving these two magnets further apart and changing the strength of the field. Okay? And what we know is that the current always flows in such a way as to try to counteract the change that it's experiencing. So as you move it or you move the magnets and it experiences the field getting weaker, that experiencing a field getting weaker is going to cause the wire to make the current flow in such a direction as to try to restore the field to what it was. It doesn't like change. Okay, but before we go there, it must be time for a little confession. So the equation that we got yesterday, that force they called was the EMF, the electromotive force, the force that they said would come out of the palm of your hand. And yesterday we found that EMF was equal to BLV sine theta. And at the end of class, I asked you to prove the units. So Tesla meters times meters per second. Well, we know a Tesla from F equals BIL sine theta. B is equal to F over IL. So we know a Tesla then is equal to a Newton over an amp meter. So Newton over an amp meter times a meter per second. The meters are going to cancel. And if we look at this, then we have a Newton meter over an amp second. And I said a minute ago, time for confessions. Time for confessions because a Newton meter, if you think of work equal to F delta D cos theta, a Newton meter is really a joule. So we could replace this top part with a joule. And an amp second, if you think of I equals Q over delta T, an amp is equal to a coulomb per second. So an amp second is a coulomb. So this is really a joule over a coulomb. I set you up because a joule over a coulomb is never going to get you to a Newton. Go back to that equation that we've used a fair bit in this unit. V is equal to W over Q. Work is measured in joules. Charge is measured in coulombs. Voltage is measured in volts. They called this the electromotive force, but it's not a force. It's actually a potential difference. So even though they thought of it as a force, and even though we still call it an electromotive force, it's a potential difference. It's a voltage that's being created when we move a wire in a magnetic field. So we still, to this day, call it an electromotive force, but it isn't a force. It's a potential difference, and it's measured in volts. And I purposely didn't tell you that yesterday because I wanted you to play with the units. Okay? But if you did your homework question, you probably just figure out volts because they probably would have given it to you at one point. Okay, so one thing that I needed to fix from yesterday that I left on purpose was electromotive force is a potential difference. The second thing was what I said there, and I don't really need to fix it, but what I said there a minute ago was the current's always going to flow in such a way to try to restore the field. So if I move this wire out of the field's getting weaker. So the current in this wire is going to flow in such a way to try to restore the stronger field. And so if I move the current out, the wire out, it's moving that way. The field lines, it must be a north on the top. I just can't quite see. Maybe if I make it bigger. Yeah, that is a north on the top if I make it bigger. So my hand would be up and down. I'm moving the wire out. And this sheet, I did conventional electron current on this. Just because, okay. So the current's going to flow in such a way to try to strengthen the field, to try to make these field lines so that when you curl your finger, I gotta switch hands. When you curl your finger around this wire, maybe it's not going to. They'll make the field stronger again. Like, so as I pull this wire away and it comes out here, the field's weaker out here outside the magnet, and it doesn't like that. So it tries to flow in such a way to have the field around the wire match the field that was inside the magnet to strengthen it. Let me flip the page. There's a better picture over here. Oops. Come on. Let me go smaller here. There we go. All right. So this picture. All right. So maybe let me just do my own picture. So this principle is kind of like that person that never likes anything. You know, that person that nothing is ever good? So if I have a north, I have a south, I have a wire, and I'm going to move the wire down. I'm going to use conventional current because that's the hand I have free. So as I move the wire down, and it's conventional current, fingers go from north to south, thumb goes towards the bottom of the page, the current is going to come out of the page. Okay? So this is what the hand rule tells us. But let's imagine that I have a magnet here with the north, and let's imagine that I have a solenoid. Watching the time, I'm probably going to run out here, but I wrap a wire around a solenoid, okay? And it's hooked up to an ammeter or a galvanometer. And it's coming down in the back. You just can't tell because I did a lousy drawing. So if I move this magnet closer, the field's getting stronger. And this wire that's not connected to any power supply doesn't like the fact that the north is getting closer and the field lines are getting stronger. So it's going to set up a current in itself to try to put a north here, to try to prevent this north from coming closer, to prevent the field from getting stronger. So then if you take your right hand and you want a north on this side, your thumb has to be over here, curl your finger